Forrest asked me to talk about Boreas, but I'm going to talk about Forrest. I started actually my remote sensing work with on 5 experiment as a 5 follow-on when I was at Goddard in '89 and till '91. At the end, I got my first proposal was on 5 follow-on, looking at soil moisture and vegetation water content. And then I moved to JPL, and the Boreas experiment started, and I really wanted to have a proposals and get involved in the experiment, because while I was at Goddard, from Forrest and peers who were actually in the same building that I was working, I heard a lot of stories about field experiments. And I thought that would be a great way to learn from others, and also be able to, since I was doing a lot of electromagnetic modeling, to just relate whatever I'm doing to field measurements. So what I like to do is to present not just my own work, but the work that a bunch of people in Boreas did using microwave sensors, especially radar. So I'm going to give you a brief overall objectives of the projects that were involved, and mainly cover 3 basically science projects. One of them was forest structure and above ground biomass density. The other one was on the soil moisture and canopy water content. And the last one was kind of looking at phenology and also freeze and thaw cycles. So before we went to the Boreas experiment, around early 90s, papers on how radar can provide information on structure or moisture were coming out. And we knew theoretically that a system, a microwave system that has wavelengths around centimeters to a meter, can have more penetration into the vegetation. And of course, everybody was saying, since we're not sensitive to clouds, so we can always look at the surface anytime we want, day and night. So that was one motivation. But we knew very basic that our measurements, we're an active system, our measurements basically interact with forest structures and surface. We had some radiative transfer models and electromagnetic model that related all of these things together, but there were very little experiments to really connect these things to measurements on the ground. And so this was our basically knowledge when we went to Boreas experiment. There were several proposals that used radar. The ones that I thought that was most relevant were the RSS-13, which was the Passat-Gogini's helicopter-based scatterometry measurements in different frequencies, and he was interested in snow and also vegetation. It was John Ranson from Goddard and his group, including Roger Lang from George Washington University, who was my PhD advisor, looking at distribution of the structure of the forest and above ground biomass. And my proposal, jointly with Mahta Muqaddam at JPL and Ted Egmont, who was at the head of the hydrology group at Goddard, was looking at the hydrology-related information from radar. And then we had Joby Way and Rainer Zimmerman, Eric Rignot, and Gordon Bonin looking at measurements through time and relating the phenology and state of the vegetation and bringing them to look at the fluxes and maybe include them in the model. And then Joseph Siller at CCRS also was interested in the land cover observations, and then Canadian also brought their own radar and flew, I think maybe one season or twice, 94 maybe or 95 in Boreas. So when we started, we had very little experience on the ground. And we were very young, clueless, especially since the first meetings that we were at, science meeting at Boreas, somebody called the remotely sensible science, and another person called us remotely sensitive. And we thought that everybody knows what they're doing except us. And because we just know theoretically what we're going to measure, we don't know exactly how the people in the field do these things. So eventually we found out through Boreas, and even now you hear that a lot of us were new to this thing and we were trying to discover. So we got really excited. And we wanted to be in the field in every season. And even our project was not so much related to winter, but Mahta and I went to winter also. We tried to do field work in winter to see exactly what are the changes we see. The AirSAR team at JPL was a big team. And they had the instruments in DC-8, which was a big plane. And we had a radar that worked in 3 frequencies at C-band, L-band, and P-band. These are the antennas on the side of the aircraft. And this was the picture of the crew. Some of them are engineers, are retired now. They're no longer at JPL, but preparing the AirSAR before going to the field. And at that time, the system was new. It had few experiences. And we always had to calibrate the system to make sure the measurements are well calibrated. So in those days, nowadays we don't do that with the radar measurements. But in those days, we had to get these big reflectors, corner reflectors. And the sizes of them varied based on the frequency, since we had even P-band system, which are 70 centimeter in wavelength. We had to use big targets. And we shipped almost 10 of these things to Southern Study Area and deployed them in different areas, oriented towards the directions that the radar looks at the ground. And we had to well position them in the angle. And later on, when we used them, we always stored them between the missions in a barn that belonged to a farmer there. And eventually he asked us if we could keep this because he really liked these corner reflectors. So eventually we gave him as a gift, and all of these aluminum metals, he loved it. And so he kept our targets. So when we flew and collected data, the images look great, and we were able to calibrate them. These are all 3 frequencies we had. This is the old Jack Pine site here in the Southern Study Area. And we had all polarizations, 3 frequencies at different wavelengths. And you can see exactly the different features come over these landscapes. So one of the interesting thing, Scott was saying that we chose all these homogeneous sites. What we saw in the images right away was it was so heterogeneous. And all of these forest stands were supposed to be even aged, and it looked very different. We were seeing different things. So we really had to go to the field and to see exactly where these variabilities come from. And when you go to the field, you really think that things are homogeneous. All the stands, trees are almost similar size, similar height, except maybe different ages. But one thing that came out, and that was one of our publications that we show, that these homogeneous stands were 2 groups, the Boreas group and also Forestry Canada, put plots in them, exactly the same plots of the main and auxiliary plots, and they did the measurements and converted the measurements to above ground biomass. And for the same stand, this was the variability between the 2 measurements on the ground. So we right away knew that there were differences. And this heterogeneity came from plots being different size and different areas, the allometry equations that they were using to convert these measurements into biomass were different. And eventually, the teams had to come together to really work out to see where these differences are coming from. And that was one of the nice meetings that we had in the, during the Boreas. So when we saw these things, we had to think about how to model the forest and interpret the radar. We knew, as I said, that the radar has sensitivity to above ground biomass and also soil moisture, because in the microwave frequency, it interacts the water with the, in the vegetation and the soil. And as the vegetation biomass increases, the sensitivity to the soil moisture decreases because it kind of blocks the moisture. This is what we really knew. But when you think about gaps are important, it comes in here that as you have gaps in the forest, the interaction of the microwave waves energy with the vegetation and soil can have multiple interactions that can bring soil information into the picture even when the vegetation is extremely dense. That you really do not block the soil so much, but you interact always with the soil. And we had to decipher this and bringing it into our models. So we developed a physically based model similar to radiative transfer models. We had to separate the soil and we had to separate the tree stems and canopy because structurally they were different. They have oriented differently and they interacted with the radar differently. And we used some ancillary data sets, built a semi-empirical algorithm and applied it to the modeling grid site in Boreas, both in the southern study area and northern study areas, and developed maps at high resolution, around 30 meters, of forest biomass at both stem and the crown, separating them. And we validated it with the ground data. And this was a good result. And we had this thing produced and we delivered it. And since we decided to work with the modeling group to tell us exactly what they need and how these scaling that Piers and Forrest had been mentioning works, we got interacted with the modeling group and tried to see what we learned from how these products would be work in the model. We also worked with the satellite data. We tried to use existing satellite at the time. Japanese had a radar satellite at L-band, radar sat, the Canadians had the ERS, the Europeans had the C-band satellite, and we worked with that satellite. John Ranson basically led some of this work and developed also from the satellite estimates of forest above ground biomass at high resolution and also a land cover map, vegetation map over the areas. And you can see the basically accuracy assessment of these measurements. Around the same time, this is actually the result from CERC. I remember in '94, the space shuttle had another mission with JPL and DLR, the German space agency, together, and they flew radar in the space shuttle both in April and October. And we made sure that we get a lot of data over the Boreas sites, and we used that, and there was a lot of publications out of that. And this is one of them that has been published by John Ranson's group, and we also collaborated with them. And one nice thing that comes from this results that you see again that there is a large scale variability of the vegetation structure and biomass over the landscape, but there is also a lot of these salt and pepper heterogeneity of forest structure. And that's very important thing. So if you even aggregate the system into 100 meter or 1 hectare, you still see a large scale or a small scale heterogeneity over the landscape. So that ended up with us trying to figure out how we can use these measurements and try to come up with a way to develop algorithms and also build satellites for monitoring the forest biomass in space. And one of them is actually the new mission that NASA is developing, NISAR, with the Indian Space Agency, which has 2-frequency radar on it. And it's going to be extremely useful, especially for boreal forest, because we have a very good sensitivity to above-ground biomass for the boreal ecosystems. And this is the results that combines the L-band backscatter from the Japanese spaceborne radar and the glass LiDAR data, derived biomass from glass LiDAR data over the boreal zone, and you really see the nice relationship. So that's one of the things that we actually learned how to do this thing from the Boreas experiments. The next thing was just bringing these measurements into the model. So we teamed up with the group in Montana, and John Kimball worked with us and aggregated the biomass and LAI and vegetation map from the radar and put it in the Biome BGC. And one thing that came out of that result was the heterogeneity of the surface. The spatial complexity of the surface was extremely important, both in the evapotranspiration estimation from simulation from model, and then also MPP. So that was one interesting result. And the biomass and LI heterogeneity definitely controlled the flux variability over the modeling grid site. And it was important that when you scale it up to larger scale, you notice that you would increase the error in terms of matching your flux measurements with the tower measurements or other modeling, larger scale modeling grid sites. So heterogeneity, or somehow bringing that heterogeneity in model, was very important. They did another experiment, and that experiment was to look at the to see if what is important in terms of heterogeneity or functional traits like deciduousness or conifer, and they noticed that the heterogeneity was more important than the deciduousness or conifer or needle leaf for the modeling. So I'm going to just show one more results on the freeze and thaw. These are the things that actually was covered by Richard Coenga, so I'm not going to mention this. Another important thing that came out of this Boreas experiment was looking at the freeze and thaw. And we knew that the soil temperature measurement had a very nice relationship with the time that actually the thaw happens and the photosynthetic activities happens, and then the carbon uptake starts. Some of the satellite measurements, such as the JERS1 data, also multiple times showed that we can detect the soil moisture or surface moisture changes that relates to the time of the thawing or the time of the freezing. And that ended up to basically doing some interesting measurements that the Kyle McDonald group and John Kimball and others did during the experiment, Boreas experiment. They built a system that they measured the dielectric constant of the trees and the xylem water flow in the trees through several seasons. And the result of that was very interesting, because it showed that both the water in the trees and the canopy at different microwave frequencies can capture the seasonality and diurnal variations of the water flow. And they can also pick up the freeze and thaw in the vegetation from these measurements. And then it resulted into developing models to relate the microwave measurements from the satellite, both passive and active, to detect the freeze and thaw. And this is one of the papers that came out to do this thing and then applying it over the entire boreal zone to show over time how much the freeze and thaw cycle or the growing season has changed. And then this experiment was also done at L-band frequency, both at the passive and the active, both radar and radiometer, and showed that they both have very strong relationship with the freeze and thaw cycle. So if you can derive or build a model that can detect the changes of the state at the time of the thaw and at the time of freezing, you can basically pick up the growing season. And then SMAP satellite, when it was built, it was actually used all this information from Boreas experiment. And right now there is a routinely produced freeze and thaw products from the SMAP measurement. So last but not least is what we learned from our radar experiment in Boreas was heterogeneity was important. The variability of the surface important. And looking at the surface at different resolutions for us was important to develop our algorithms and models. The next thing was we learned a little bit more about uncertainty, and that was because there was a lot of good ground measurements to help us to really understand what are the errors in our algorithms. And the last thing was the scaling, which basically helped us to understand that how can we scale our measurements to deriving biomass or any other type of information from one scale to another. And the results of that actually has been translated in developing these new remote sensing techniques for space missions. That's it. Okay.